All right, thermodynamic processes. We're going to talk about the different processes when you have a gas and it's in a closed environment like a piston. The types of graphs that you can get. So we've talked about PV graphs, and now there are different processes that occur. Things like heat engines or refrigerators. And so we have four basic types of thermodynamic processes. There we go. First, we'll talk about something called isovolumetric. It's also called isochoric. Iso, that little prefix, means constant or unchanging. So this is a process whereby volume does not change. And we've seen this before on graphs where if you have a vertical line, right, that means that on the x-axis, which is your volume. If you have a vertical line, then your volume does not change. Okay. So if volume doesn't change, then work is zero. Work equals negative PV. So if volume doesn't change and your work ends up being zero, how does that affect the first law? Well, U equals Q plus W. If there's no W, then it's just U equals Q. So what happens is for each one of these processes, you have certain things that occur. Some things stay the same, some things change, and so it changes what happens to the first law. Okay. So for isovolumetric, all of the energy is absorbed. All the energy absorbed by a system will go into increasing the internal energy of that system. Okay. So I think I've shown you this graph in the past. So this is what happens. Heating at constant volume. And of course, it depends on which way you go, right? If we start down here and go to here, then we had to heat something. Or if you start up here at the top and you go down to here, your pressure drops, but volume stays the same. And so you have to cool something. So this is called isovolumetric, and it's represented by a vertical line. Next process is called isothermal. Isothermal is where thermal is in temperature, right? Iso meaning to not change. So this is where temperature stays constant. So think about if we have a gas in a cylinder with a piston and you want the temperature to stay constant for that gas, what would you have to do? So when temperature is constant, your change in internal energy does not change. Your internal energy, doesn't change. If temperature stays constant, temperature is a measure of internal energy. We're talking about the kinetic energy of all of those atoms and molecules. So if temperature doesn't change, then internal energy doesn't change, right? So the equation is U equals Q plus W. And if you have no change in U, that ends up being zero. And so you end up with Q plus W. So Q would be equal to negative W. So the heat added is equal to the negative work done, or vice versa. So all of the energy absorbed by a system is converted into work. So an isotherm is this line right here is called an isotherm. And so an isothermal process is anywhere along this line. We could start at, this could be state A and this could be state B. We could go from A to B. We could go from B to A. Right? And you got to remember what happens when we go left to right or right to left. Right? Well, we have a volume change. And it doesn't really matter how you get there. If you have if you start here at a small volume and you end up at a larger one, it doesn't matter whether you go this way down like this or this way up like that. Okay, so you ask yourself what's going on with the volume. Is it getting bigger or is it getting smaller? And you can think about what's happening to the gas. Pushing the piston down, is it being pushed up? Okay, so this is an example of something called an isothermal process. And what that would mean is that the temperatures anywhere along this line are the same because it's called isothermal. work done would be the area under that curve. Now, since it's a curve, they're not going to ask you to actually calculate the work done, but they can ask you concept questions involving this. Okay. Third process is called isobaric or isobaric. Depends on how you want to pronounce that. Isobaric. Iso meaning the same, baric meaning pressure. A lot of times when you watch the news, you'll hear the weather guy talking about barometric pressure. He's talking about pressure. Okay? So this is where pressure stays constant. And this is where on the graph you have those horizontal lines, because pressure is on your y-axis. So you'll have these lines going left and right. Right? So what happens here? Pressure stays constant. Yes? Okay. Now, your pressure is constant. Your volume can change. Volume can either get bigger or smaller. So you can have work done because your volume can go up or down. But you will have a flat line because pressure stays constant that whole time. You need to think about what happens here. If volume gets bigger or if it gets smaller, but my pressure doesn't change, what's going on with that gas? And we can invoke the entire first law. So an isobaric process will be a flat line somewhere on this graph. And the area under that curve is the work done. And you could calculate this because this is going to be some type of a square shape. And so they may ask you to do that. The last process is called adiabatic. And this is where something happens so fast that there's no there is no transfer of heat from one place to another because something happens so fast. Okay. And so there is no exchange of heat. So Q is 0. So in the first law, U equals Q plus W. Well, Q is equal to 0, so all you have left is U is equal to work. Right? So this is what happens inside of diesel engines. Diesel engines in trucks and some cars, they have no spark plugs because we compress that air-gas mixture so much and so fast that it ignites itself. And this is what happens. This decrease in internal energy, right? So internal energy usually drops, and therefore you have a decrease in temperature. So here is our high temperature isotherm right there. Here's a low temp one. Usually on a graph I would just give you maybe one isotherm, and then you have something called the adiabatic curve. And so you'll see something like that. Oftentimes, all the time, these two curves are joined up here at the top, but then they are usually different at the bottom. Now here are some examples. So isobaric, you have that flat line because pressure doesn't change. Isovolumetric is where your volume doesn't change. So these are the easy ones. Okay, here work is 0 because there is no area under the curve. Here you can calculate work and it will be that square shape. Here's an isotherm. So this is an isothermal process from A to B or B to A. And all the temperatures along this curve are the same. And this is called adiabatic. And it will end up at a lower temperature than an isotherm. And so what happens is they can actually put this into a full graph where you have different processes happening, and they'll say, well, what's going on at different places along this graph, right? We can go from A to B to D, or A to D to B, or A to D to B to A. And so they'll say, well, from A to B, what is that process? They can ask you questions about temperature, things like this. No, there we go. So here's an example of an adiabatic process. Right? This is a fire extinguisher. So what happens is gas expands when it comes out, right? The temperature drops, so this canister would actually feel cold. Okay, so here are some examples of what's happening in different processes. We have adiabatic. We have a couple different isotherms. Sometimes we just have one, and then this line here is what they call the adiabat. And so this is where we could have something where we do work, right? Maybe the gas does work on this piston, and it happens so fast. We have a positive volume change, and so you'll actually get a drop in temperature, is what happens. And that's what it shows on the graph here. So this is called isometric or isovolumetric, and this is the line that we care about right here. Maybe we have some isotherms. Sometimes you just have one. Sometimes I just show you this vertical line. This is where your volume stays constant, right? So we don't move the piston in or out. Volume is constant. So heat will go in or out, right? Pressure goes up or down, depending on whether you're adding heat, taking heat away. Isovolumetric, sometimes it's called isometric. All right, isothermal. So this line is called your isotherm, and you can go from state 1 to state 2 or state 2 to state 1. Doesn't matter. If they ask you questions about what's the change in temperature from state 1 to state 2 or state 2 to state 1, you will say there is none. It's an isotherm. All the temperatures are the same. What changes is volumes, right? And so we can add heat, we can take heat away, and our volume will change. And that is the nature of an isotherm. One example of an isothermal system is a gas that is confined by a piston, and we don't even heat it or cool it. We can move that piston so that the gas expands or compresses. And we can maintain temperature by putting the system into contact with some sort of reservoir, right? So heat transfers, it does take place, but the temperature will stay constant. And so this reservoir could be something like a car's radiator, something like that. Isobaric is where pressure doesn't change. Here's your isobar right here. It's that flat line. So we could ask you questions about going from state 1 to state 2 or back. Your volume changes, right? And this is where the piston can move, right? Volume will change. You either get negative or positive work, depending on which way you go. You input heat to the gas and it can expand, right? But pressure stays constant. Example problem. Can you identify which path is isobaric, isothermal, isovolumetric, and adiabatic? So there's easy ones. This vertical line will be your isovolumetric process because volume doesn't change. This horizontal line D will be your isobaric process because pressure doesn't change. The other two are always a little bit harder. This sucker, C, ought to be your isotherm, and then B ought to be adiabatic. And so that's what should happen. And there you go. B is adiabatic because it ends up at a lower temp than your isotherm does. Practice problem. Can you calculate the work done on the gas? The work done is going to be the area under the curve. So you have a little rectangle and a triangle. Can you do it? Area of the triangle, area of the rectangle, I can add them up and I get my work. Now here's a question. Is that work negative or positive? This is negative work. This is work done on the gas. Best way to tell is that my volume gets larger. Last one. Can you try this? See if you can get it. There's the answer.